We're now ready to study elastic collisions. Now in this video what we'll do is set up the basic equations that will be used to study elastic collisions, and then we'll look at one example of an elastic collision and understand how to use the conditions. Now once again, if you go back to the definition of an elastic collision, in an elastic collision we know that the kinetic energy is conserved, so Ke is conserved. So if you're told in a problem that the collision is elastic, then you can assume that the kinetic energy is conserved. Now which means that Kei equals Kef. So this is one setup that you can use. Kei equals Kef makes life very easy. Okay, and another thing we can also do is, again, if there are no external forces, if no net external forces during the collision, okay, then we can also use Pi equals Pf. We can use that the momentum is also conserved. So we have two things that we'll have to figure out. Okay, typically in an elastic collision there will be two unknowns, and if you have two unknowns, we all understand that we need two equations, and those two equations will come from the two conservation principles. One will be the kinetic energy conservation, and then the other will be the momentum conservation. Okay, so let's look at an example of how to apply all this to a problem. So here's the example. Let's say that we have a block of mass 1 kg that moves to the right with a speed of, say, 10 meters per second, and let's assume that there's a second block of mass 2 kg that is at rest. So the first block is moving, the second block is initially at rest, and let us assume that the collision is elastic. So collision is elastic. So you've been told that the collision is elastic, and the question is find velocities. So let's call the velocities v1 and v2 after the collision. Okay, so let's set this problem up. Okay, and let v1 be the velocity of the 1 kg block after the collision, and v2 be the velocity of the 2 kg block after the collision. And our goal is to find v1 and v2. Like we said, we have two things that we're looking for, and we're going to have two equations. So the first thing that we'll do is we'll use Pi equals Pf. So Pi equals Pf. Let's use this. So this gives us that the total momentum in the beginning, which is the momentum of the 1 plus the momentum of the second, equals the momentum of the 1 in the end plus the momentum of the second in the end. Okay, so let's simplify this, and we can rewrite this as v1 plus 2 v2 equals 10. Alright, let's just call this equation 1. Now we need a second equation, and like we said, since the collision is elastic, the kinetic energy is conserved, so we're going to use now Kei equals Kef, and this gives me kinetic energy is 1/2 mv square, so it is 1/2 times 1 times 10 square plus 1/2 times 2 times 0 square equals 1/2 times 1 times v1 square plus 1/2 times 2 times v2 square. Now let us simplify this equation before we actually solve the two equations simultaneously. Now the one thing that we need, the tendency is to just multiply the 10 square out, you get 100 divided by 2, make it 50, and all that. But you see, it's easy to work if we just eliminate a few things. So if you look at this equation, we can get rid of all the halves first. We can divide both sides by halves, so all the halves go away. Now we can simplify. The 1 times 10 square is equal to 100. Okay, the other one is 0, and then we have v1 square plus 2 times v2 square. So this equation is much easier to deal with. So do that, get rid of all the halves, and then set the equations up properly. Alright, great. So now we have two simultaneous equations. The first one, which is this right here, and then the second one is the equation that comes out of the kinetic energy conservation. And to solve this, all we're going to do is we're going to solve for v1 from the first equation and substitute it into the second equation. So here we go. Okay, so equation 1 gives us v1 equals, the equation was what, 10 minus 2 v2. So it gives us 10 minus 2 v2. And now we can substitute into 2. So substitute for v1 into equation 2. Okay, and what we get is we get v1 square, which is 10 minus 2 v2 the whole square plus 2 v2 square is equal to 100. Great. Let's multiply all this out. Now a minus b the whole square is a square. This is 100 minus 2ab, which is 2 times 10 times 2v2 plus 4 v2 square plus 2 v2 square is equal to 100. So we have our equation simplified. Let's get rid of the 100. So the 100 goes away. We can combine the 4v2 square and the 2v2 square. That gives us 6v2 square, and then the remaining term becomes simply equal to minus 2 times 2 times 10, which is 40 v2 and equal to 0. Alright, so now let's factor out 2v2, and I get 3 times v2 minus 20 equal to 0, and this implies two things. Whenever the product of two things is 0, we know that at least one of them is 0. Okay, so either 2v2 equal to 0 or 3v2 minus 20 is equal to 0. Now what this does is, this gives me v2 equal to 0 or v2 equals 20 divided by 3 meters per second. Okay, now before we analyze anything, let's just find v1. Okay, we know that v1 is equal to 10 minus 2 times v2. Okay, so this is simply equal to 10 meters per second, or the second equation gives me v1 is equal to 10 minus 2 times 20 over 3. When you simplify this, you get minus 10 over 3 meters per second. Okay, let us see what the two solutions give us. So this is solution 1 here. I'm going to put a circle around it, and I get another solution. I'll put a blue circle around it, which is this one. Okay, so let's look at the first solution. The first solution tells us that after the collision, okay, this tells us that after the collision, v1 continues to move at 10 meters per second and v2 continues to remain at rest. So basically this means, this is telling us that there was no collision. So which is a physically valid solution. It is a valid solution because, hey, it tells us that there was no solution, if there was, no collision. And if there was no collision, then of course the objects will continue to do what they were doing. Okay, so although this is physically correct, it's not what we are interested in. We want to know what happens if there is a collision. And what this tells us is that v2 will move to the right and v1 will bounce back. So after the collision, v2, the block 2, will move to the right with 20 over 3 meters per second, and block 1 will bounce back at 10 over 3 meters per second. The negative sign just tells us that it's going to move to the left. So that's the solution that we will be looking at. Okay, so that's it for the problem. This is a quick application of the elastic collision problem. I know it's a lot of work and there is actually no way around it. Okay, you just have to do the algebra very carefully, keeping in mind that the kinetic energy is conserved, and that if the collision is like regular collisions, then the momentum is also conserved, and then we can go ahead and solve the problem. Okay, so that's an application of the elastic collision problem.